Okay, so couple things to think about, right? Atoms are 1 angstrom in size, right? They are 10 to the minus 10th meters in radius, okay? Remember that we can actually visualize something that is a 10 to the minus 4th. These little things here are 10 to the minus 3rd meters. And you can picture something that's 10 to the minus 4th. You can actually see that with your bare eyes, okay? So this is the smallest thing I would say that most of us can see. If you take one of those tenths of a millimeter and blow it up to the size of a soccer field, an atom is actually a sheet of paper, okay? It's the size, it's the thickness of a sheet of paper. That's the radius of an atom, right? So you can almost visualize that, right? And I know this because 100 sheets of paper is a centimeter, right? Therefore, 100 centimeters would be a meter, and then a million sheets of paper, if you stacked them, would be about a soccer field, right? But here's the crazy thing, right, is that the nucleus of an atom is about 10 to the minus 15th meters. So when you see pictures like this of the atom, this is ridiculous, right? This thing here is like a quarter of the size of the atom, right? No. Nuclei are 1/100,000th of the size of atoms, right? So they're just absolutely vanishingly small. You can't draw a picture of an atom. If you can see the atom, then you can't see the nucleus, right? And if you can see the nucleus, then the electrons are so far away you can't see them, right? Anyway, just a thought, right? Here's a real simple formula that lets us calculate the approximate nuclear radius, okay? And this is just based on, if we have the volume is 4/3 pi r cubed, right? So if we're solving for the radius, right? The radius is going to be the cube root of the volume times some constant, right? Which has all these things in it, right? Okay, sorry. So that's what's going on here. So A, you got to understand this is the mass number. So the mass number is the number of protons and neutrons. By the way, when they say uranium-235, uranium is, I think, element 92 or something like that, right? 235 is the total protons and neutrons, okay? So this is, when they say carbon-12, that's 12 is the mass number, okay? So the first example here is, what is the radius of a uranium nucleus? By the way, the Fermi radius is the radius of, if the mass number is 1, right, then the radius is the Fermi radius, which is the radius of a hydrogen atom, okay? Just by the way, sorry, nucleus, hydrogen nucleus, which is approximately the radius of a proton, right, because that's what it is. Anyway, let's use our formula here. Our radius is R0, mass number to the 1/3, right? So that's 1.2 times 10 to the minus 15th times the mass number, so 235 to the 1/3. We can do this. I can do it. So 1.2 times 10 to the minus 15th times 235 raised to the 1 divided by 3. This calculator makes it easy to do that. It's 7.4 femtometers. 7.4 times 10 to the minus 15th, which is a femtometer, right? 7.4 femtometers. How many femtometers? There it is. All right. I sort of have a feeling that this is an approximate formula because the nuclei, I think this nucleus is maybe a little bigger than that. They don't have the same density. Helium has a different nuclear density than uranium, a little bit. Okay, I'm just going to say. All right, enough of that.